Let's talk about pointers. Up until now, we've always just referred to things in memory explicitly by name. We've said int n equals 42, and then when we want to use the variable n, we just call it by the name we give it by writing something like n times 2. But that variable must live somewhere in memory. When you want to use the value that is currently stored inside n, or update the value that n is holding, your program needs to know where in memory to look for n. Where in memory a variable lives is called its address. It's like a house address. I can find someone's house as long as I know their home address, and a computer program can find a variable as long as it knows its memory address. What pointers provide is a way of directly dealing with these memory addresses. A lot of the power in C comes from being able to manipulate memory like this. But with great power comes great responsibility. Pointers can be used dangerously enough that a lot of programming languages hide pointers entirely. So why does C give us pointers then? As you know, arguments to a C function are always copied into the parameters of the function. So calling something like swap on some variables x and y can't interchange the values of x and y in the calling function, even though that might be handy. As we'll see later, rewriting swap to take pointers to the locations needing to be swapped allows it to affect its caller's variables. Let's walk through a relatively straightforward example of what pointers can do. Let's say we have int n equals 4 and int star pointer to n equals ampersand n. Whoa, a bit of new syntax to cover. First, let's interpret this ampersand n. Remember that everything in memory has some address. The ampersand is called the address of operator. So ampersand n refers to the address in memory where n is stored. Now we are storing this address in a new variable, pointer to n. What is the type of this new variable? The asterisk is a part of the variable's type, and we'll read the type as int star. Int star means that pointer to n is a variable that stores the address of an integer. We know that ampersand n is an int star, since n is an integer and we're taking the address of n. Int star is an example of a pointer type. As soon as you start seeing asterisks in the type, you know that you're dealing with pointers. Just like we can declare a variable as int x and char y, we can say int star z and char star w. Int star and char star are just new types for us to use. The location of the star can go anywhere before the variable name. So both int star pointer to n with the star next to int as we have here, and int star pointer to n with the star next to pointer to n are valid. But here, I'll place the star next to int. It doesn't matter which you prefer, just be consistent. Let's draw a diagram for this. We first have the variable n, which we'll draw as a little box in memory. For this example, let's say that this box is located at address 100. Inside of this box, we're storing the value 4. Now, we have a new variable, pointer to n. It has its own box in memory, which we'll say is at address 200. Inside of this box, we are storing the address of n, which we before said was 100. Frequently in diagrams, you'll see this shown as a literal arrow leaving the pointer to n box, pointing to the box that stores n. Now, what can we actually do with pointer to n? Well, if we say something like star pointer to n equals 8, This is a different use for the asterisk that is completely separate from the use of the asterisk in declaring a variable of a pointer type. Here, the asterisk is called the dereference operator. In our diagram, what star pointer to n equals 8 means is go to the box containing pointer to n, follow the arrow, and then assign to the box at the end of the arrow the value 8. This means that after this line, if we try to use n, it will have the value 8. The word pointer is used in a lot of different contexts. Here we'll try to be consistent. A pointer type is something like int star. In this video, a pointer will only be used to mean a value with a pointer type, like pointer to n, which has type int star. Anywhere we used to just say n, we can now instead say star pointer to n, and everything will work just as well. Let's walk through another simple example. Let's say we have int n equals 14, int star pointer equals ampersand n, n plus plus, and star pointer plus plus. The first line creates a new box in memory labeled n. This time we won't label the box with an explicit address, but it still has one. Inside of the box, we're storing the number 14. The next line creates a second box labeled pointer. And inside of this box, we're storing a pointer to the box labeled n. So let's draw the arrow from pointer to n. Now, n plus plus increments the value in the box labeled n. So we go from 14 to 15. Finally, star pointer plus plus goes to the box labeled pointer, dereferences the value in the box, which means follow the arrow to where it points, and increments the value stored there. So we go from 15 to 16. And that's it. N now stores the number 16 after having been incremented twice, once directly by using the variable name n, and the other through a pointer to n. Quick quiz. What do you think it means if I try to say something like ampersand, ampersand n? Well, let's rewrite this as ampersand, ampersand n parentheses, which accomplishes the same thing. The ampersand n in parentheses returns the address of the variable n in memory, but then the outer ampersand tries to return the address of the address. That's like trying to do ampersand 2. It doesn't make sense to get the address of just some number since it's not being stored in memory. Using 2 ampersands in a row is never the right idea. But now, what does it mean if I try to say int star star double pointer equals ampersand pointer? Now I'm creating a new box labeled double pointer, and inside of that box I'm storing the address of pointer, which means I draw an arrow from the double pointer box to the pointer box. Notice the type of double pointer, an int star star. N was an integer. Pointer stored the address of n, and so has type int star. Now, double pointer stores the address of pointer, So it has type int star star. So what do we think this means? Star star, double pointer, equals 23. Notice that I'm now dereferencing twice. Just follow the box and arrow diagram we've already set up. First, we go to the box labeled double pointer. The first star means follow the arrow once. Now we are at the box labeled pointer. Now the second star says follow the arrow again. And now we're at the box labeled n, and we set the value of this box to 23. Notice that the dereference and address of operators are inverses of one another. This allows me to do something like star ampersand n equals 42. While this works, you should never do something like this in practice. What are we actually doing here? The first ampersand grabs the address of the variable n. Then we have a dereference operator, which means we are going to that address in memory. So we're back at n. Now we grab the address of n again and immediately dereference. So we're back at n and store 42. So each pair of star ampersand just cancels out. There's a special pointer called the null pointer. This is a pointer that we should never dereference. Such a pointer is important because it gives us a way to distinguish between a pointer that should and should not be dereferenced. If you try to dereference a null pointer, typically your program will crash with a segmentation fault, which you may have seen before. So let's say we have the code int star x equals null, star x equals 4. In this example, it may seem obvious that we're doing something bad, but remember that null could really be a value returned from a call to a function, like malloc if malloc is unable to allocate the memory requested by the user. For this reason, if instead we set the value of x from a call to malloc, as in int star x equals malloc, size of int, then we should always explicitly check to see if null was returned. If x equals null, return. Else we can continue on and say star x equals 4. So again, why should we ever use pointers? Let's look at an example of a program where we need to use pointers. A simple swap function. Let's say I have two integers, int x equals 4 and int y equals 15. And I want to write a function called swap that I can use like so. Swap x, comma, y. After this line, the values inside of the variable x should be 15, and the value inside variable y should be 4. The values inside of x and y have been swapped. Without pointers, we might try something like void swap int a, int b, int temp equals b, b equals a equals temp. But do you notice the problem with this? Remember that the value stored in the variable a is just a copy of the value of x, and the value in b is copied from y. Any changes made to a and b will not be reflected in x and y. So while the values of a and b are correctly swapped, x and y haven't changed at all. Now let's change the swap function so that its arguments are pointers to the variables it should swap, like so. Int star a, int star b, int temp equals star b equals star a equals temp. Remember that swap's arguments are now pointers, and so we need to pass the address of x and y in the call to swap, like so. Swap $x, comma, $y. This now correctly swaps the values of x and y. Let's draw a box and arrow diagram to see why this works. We start with our two boxes in memory, x and y. Inside of the box for x is the number 4. And inside of the box for y, we have 15. Now, inside of the call to the swap function, we have two more boxes for the arguments a and b. A points to the box for x, and b points to the box for y. A new box is created for the variable temp, and inside of it, we store the result of dereferencing b, which means follow the arrow from the box labeled b. So we store 15 inside of temp. Then we follow the arrow at b and store here the result of dereferencing a, which is the value 4. Finally, we follow the arrow at a and store what's currently inside of temp, which is 15. Notice that the boxes labeled x and y have correctly swapped values. Once we learn more about malloc and dynamic memory management, we'll see that we have no choice but to use pointers. Walking through the box and arrow diagram for any program can help you figure out what the program is really doing. My name is Rob Bowden, and this is CS50. This is a different use for the asterisk. I hate that word. Anywhere we used to just say n, we can now say pointer to n. No, you can't. Star pointer to n.